Okay, so today, lecture 10, we're going to talk about VLIW architectures. So this is quite a shift. Now we've looked at traditional ISAs, superscalar implementations of those ISAs, adding vector units. And this is a different approach to getting increased performance. So if you look at a regular instruction set, it's really encoded as a sequential ISA. That means the semantics of the instructions are you do one instruction to completion, then you move on to the next instruction, and that's the way the instruction set is specified. So if you look at what happens in compiling code for a conventional superscalar, you start off with a sequential source code. Superscalar compiler then looks at that source code, breaks it down into independent operations, and then tries to find the parallelism between those operations and schedules them in some order, and comes up with a parallel schedule. But having looked at the sequential source code, it then has to produce a binary for the sequential ISA. So it then schedules them and emits sequential machine code. So it's done the work of analyzing the instructions, figuring out whether they're independent, how they're independent, figuring out how to schedule them to run in parallel. But then it packs it out into a sequential machine code form. And then that sequential machine code, you then feed into a superscalar processor. The first thing which that does is then look at that sequential machine code, effectively extract the parallelism from that sequential instruction stream, and then schedule things for execution in a parallel way. So it's clear there's a bunch of redundancy here, right? So the compiler's done this work of finding independent operations and schedule them for execution, but it then has to encode that in sequential machine code. So then when the code actually executes, you have to then, the hardware is rechecking for those dependencies and then rescheduling things on the fly. So the idea came along of why not just do this one step and go straight from the compiler doing this work of scheduling and then actually go direct to execution with the compiler schedule of those parallel operations, right? So that's basically the idea behind VLIW machines. So in the classic VLIW machine, purest expression of this, all the scheduling and all the hazard handling is done by software in the compiler. And so the machine just has a very long instruction word which represents all the operations that can initiate execution on the same clock cycle. And so here's a very simple example machine where there are 6 slots to do different operations. So this is one instruction with 6 slots. So the first 2 slots can be used for integer operations, and they have a single cycle latency. The next 2 operations are memory operations, loads of stores, and they have a 3 cycle latency. And then the 2 floating point units are added here with a 4 cycle latency. So the ISA spec of this machine has all these hazards encoded. So they say that this memory operation you cannot use as a result for 3 cycles. And so the compiler has to insert no op fields at those slots in each instruction if it can't find anything else to do while waiting for the result. The compiler also has to guarantee there's no dependency between these operations. Obviously, they're going to happen at the same time. And so it really puts a big burden on the compiler to do all this work, but it makes the hardware be extremely simple. And in fact, this hardware looks a lot like the microcode engines inside earlier machines, where everything was done, in that case, by the architects writing the microcode. But here now the plan is to take regular source code and compile it down to this VLIW, which looks a lot like horizontal microcode. That's kind of the start of the machine. So the sort of earliest style of machine in this style was the floating point systems AP120B. And this was sold as an attached processor. So it was an accelerator for a regular processor. So the idea of accelerators is very old. It goes back a long time. And this is an early example. And the way you use this machine was they provided it with a bunch of hand-coded math libraries. So you buy this thing, you would use the libraries, you would code your application in terms of those pre-existing libraries that drove this array processor. But with this machine, everything was done using hand-coded libraries. So the notion was the human was sitting there writing those loops for this VLIW accelerator and just building up this library of routines you could call from the big application, main application. But this idea of VLIW, it really took off as people evolved the compiler technology to make it possible to have a compiler look at general source code and translate it down into good schedules for these machines. But we'll talk about software pipelining and loop unrolling, which are 2 of the main sort of software mapping techniques people use to get good performance on loops. But for more general purpose code, the idea of trace scheduling was really what led to people thinking about using VLIW in a more general purpose setting, not just for loops. So these two machines came out sort of a decade later. The multifold trace came out of Josh Fisher's group at Yale, and the Cider 5 was Bob Rao's machine. Both these are very wide machines. For example, the trace was up to 1024 bits of instruction words, so doing 28 operations in one instruction. So that was a very wide machine. Okay, so what does a compiler have to do? So the VLIW compiler is responsible for scheduling operations to maximize parallel execution. It's also guaranteeing that there's parallelism between the operations inside a single instruction, and it has to also schedule to avoid data hazards. So it's actually adding explicit no-ops between instructions. So let's look at loop execution. Here's a little vector add loop. We're adding a scalar to a vector to produce another vector. Simple piece of C code. Here's the loop translated into scalar assembly code. And what we're going to do is take these scalar operations and map them into VLIW instruction slots. And here's our machine. So each column represents one of the functional units in the machine. Time runs down here. So each one of these thick boxes is a single VLIW instruction. So when you start mapping this, you say, okay, let's take the first instruction, floating point load. We place that in this slot. That's a memory operation. The next instruction is this add that bumps the pointer, the address pointer x1. Now, one thing that might seem a little odd is this is updating x1. This floating point load is using x1. So now the first question you should have is it correct to put that add in the same instruction as the load? So what's the issue here? Yep. Right after read, right. So this guy is going to overwrite the value of x1, and this guy is trying to read. So this is one of the common issues in VLIW machines. You have to kind of specify how the operands are read or written within one VLIW instruction. If you think about building the hardware for this machine, the obvious thing to do is that as you fetch and decode the whole VLIW instruction, you're going to then go through the register file read stage, and so all the instructions will read their operands, then they will do their execute the operations, and then produce results they will write back. So if you have that classic simple pipeline structure in mind, then this would be okay to specify that it's okay for instructions to write registers that other operations in the same instruction read, because the writes will happen later than the reads, because all the reads will happen just after decode as you issue that instruction. So this load will use the old value of x1, and this add will overwrite that x1 sometime later. Okay, and that would be a standard thing you do in a classic VLIW machine to allow overwrite. And so you could actually have two instructions that swapped two registers where the two instructions read the register and wrote the other register, and that would be legal in one instruction in that style of machine. So let's just assume you can do that for now. So then the add can be scheduled up here in that first instruction. So the next operation is a floating point add, but in our machine, the loads have a 3-cycle latency. So you cannot schedule this add until quite a bit later, right? So the floating point add pipeline is here. The compiler has to explicitly insert no ops until the add is ready. And finally, you have a store of that result, and that has to wait for the add to produce the result, which has a 4-cycle latency. So now this is the dependency, the read after write dependency for the store data. So it can only be scheduled all the way down here. Now you have a couple of pointer updates to do as well. Pointer update on the x2 pointer, and you have to check the branch condition. Have you reached the end of the array? Those can be scheduled, as we talked about before. This address update can happen in the same cycle as the store uses the address. And the branch can also be scheduled in parallel here. So you found some parallelism in this code, but the thing to note is there's just a lot of empty space, right? So, and in a classic VLIW machine, all that empty space is encoded as no ops in those instruction fields, right? So you've removed all the interlocking and hazard checking hardware from the hardware, but the trade-off now is I've massively expanded the instruction space and the instruction fetch bandwidth that I need to support a given machine. In effect, you're fetching these no ops from RAM instruction ROM instead of reconstruct them on the fly by doing dynamic checking on the hazards, right? So, and also in this case, you'll notice that the performance is pretty lousy. Like, you know, you're only getting one floating point add every 8 cycles. So it's very low efficiency in this case to execute the loop this way. So you don't want to just do this, and this is where the ideas in the FPS system evolved of doing, one thing you can do is loop unrolling. So the idea of loop unrolling is instead of doing 1 iteration at a time, actually do 4 iterations at a time. So if you take this original C code and then manually unroll the C code, it would look like this. You would have, you know, 4 elements at a time in each iteration of the loop, and now the loop increments by 4 each time. Now this version of the code is equivalent to this version, except that we have to handle any remainders, groups of less than 4. Notice we write BI here before we read AI here, which is fine. But to get better performance, you have to analyze the memory access pattern in the code and figure out that it might be safe to actually reschedule this store of B later than this load from A. If you can determine A and B arrays don't overlap, you can do better. And that's what's assumed if you look at this piece of code, which is taking that C code, mapping it down to optimized assembly code. So this optimized assembly code, we now have the 4 loads for the 4 iterations happening first, and the 4 stores happening later. So that assumes you know it's safe to move the load from the second iteration up here before the store from the first iteration, right? So you've done that hazard detection at compile time. Assuming you can do that, you can produce this loop and roll schedule. So now you have 4 loads that are going off in parallel. Notice the other thing you can do is you can fold the pointer update. Instead of having increment the address pointer each time, you can fold that instead, add it to the offset. So you're bumping the offset instead of actually bumping X1. Then you only need to bump X1, the pointer, once here with an add. Okay, so you do the 4 loads, you then do the 4 floating point adds, then you do the 4 stores, and then you have a single loop back as well. So as well as giving you more parallelism, you've also reduced overhead. You've cut out some of the instructions you would need dynamically to execute the loop 1 iteration at a time. So now let's look at scheduling this. So when you put the first load down, you can now just pipeline the other 4 loads going one after another. So you get much better utilization out of the load pipe. And you have the single pointer update here. Now scheduling the floating point adds, they can all just be done as soon as the value is ready from here. I can do the first floating point add, and then the other ones just follow right after in the pipeline, 1 cycle later as the load values return. Then finally I can schedule the store data. As soon as the first element's ready, I can do this. Then I can also schedule in the store data for the other iterations of the original loop. And finally, there's just 1 pointer update and 1 branch check at the end. Okay, so now this is substantially better than the previous code. You got almost 4 times as much work being done here by doing this loop unrolling. But it's still not that great. You're only about 1/3 of peak efficiency on this simple loop, right? And you notice there's still a lot of white space in here. So loop unrolling by itself helps, but you know, you're still kind of fundamentally limited by these sort of latencies through the main functional units. So another technique people came up with to help even more is what's called software pipelining. So with software pipelining, what you do is, well, let's start with that unrolled code first to get that level of parallelism. And now what we start doing is let's just schedule each pass through this loop. Instead of trying to build a loop, we'll just lay it down one after the other as if we were just going to do it all in one single basic block, right? So this is the first iteration laid down. I made a slight adjustment in that I scheduled this add 1 cycle later than it needed to be. And you'll see that's just needed to make the code cleaner when I'm done, right? But this is a safe thing to do. I've just delayed the add by 1 cycle over the minimum where it could be executed, right? So here's the 4 loads, the 4 adds, 4 stores, the pointer update. That's 1 iteration of the unrolled loop. Let's do the second iteration now and just write this in green. So this is the second iteration of the unrolled loop. And I've now pushed that in to happen as soon as it can after the first iteration. So now the loads for the the green iteration are happening right after the loads for the purple iteration, right? In this design, in this layout. Okay, now I'll do that again. And here's a red. The third iteration is in red, and here's the 4 loads for that third iteration, the adds and then the store. So all I've done is schedule the second and third loop unrolled code sets right after the other ones without worrying about where's the loop going to be, right? So let's ignore the branches. Well, if you look at it carefully, what you determine is actually here is a body of code, just these 4 VLIW instructions, and I can actually just iterate around those. And so what you have is what's called a loop prologue, and what this is doing is loading up the software pipeline. And the software pipeline is called a software pipeline because it's not a hardware artifact, it's an instruction scheduling artifact the software creates, where within this loop, I'm doing loads for the newest iteration while I do adds for the next oldest iteration, and finally stores for the initial iteration, right? So I start off, this is the first iteration of the loop. So I'm just draining that last stage of the pipeline. So the software pipeline here is load, add, store. So load, add, store is happening all at the same time, but for different iterations within these 4 instructions inside that loop body. All right, so while I'm storing for the oldest, I'm adding for the next oldest and loading for the newest, all in the same set of 4 instructions. And this is how I load up the pipeline with the correct values. And finally, when I'm done, I have to drain the pipeline with the correct values at the end, okay? So this gives you, both this code is very dense and also is very efficient, and you're basically getting 100% utilization in the middle of that loop. Now, some things to bear in mind is, like, if you do this load here, load into F1, this is actually overriding, this will overwrite the F1 that this add is using. Notice here we have load into F1. You then do fadd using F1 as a source. So this load overrides the input to this guy. But as we said, you know, with the read after write hazard, the write after read hazard structure, it's okay to write a register that another instruction reads in the same, another operation reads in the same VLIW instruction, okay? So this guy will overwrite the operand to this guy at the end, and then it'll be ready for next time around the loop to write it here. Notice the latency as well is 4 cycles. So this load here only takes 3 cycles to be ready, so it will be ready by the time it's consumed by the add, the next iteration around the loop. And the same, the add result is produced and is ready to be stored when you come around to the next iteration of the loop. Okay, so this is software pipelines. This is a very critical technique for getting good performance out of loops on a VLIW machine, and in fact for any superscalar style machine. So these ideas of loop enrolling, software pipelining, they're essential for loop performance of VLIWs. They're also useful for getting good performance on in-order superscalars, or even superscalars that are out of order or register renaming. You can actually reduce the, increase the parallelism of the code and reduce the pressure on the resources inside of an out of order core by doing this code scheduling before you give it to the out of order core. Okay, so that's software pipelining. Now, just to contrast just loop enrolling with software pipelining, the way to think about loop enrolling, you have this single unrolled loop iteration, but there's some overhead to get the data going. Then you do a bunch of work and then you write it out. Then you jump back again and start it all again for the next group of elements. So every group of elements, you kind of face the startup overhead, the execution time, then the wind down. With software pipelining, you overlap the startup and wind down of different loop iterations in the same body, the same code body. Right, so you kind of can sustain high performance. With loop and roll, and you're kind of always hitting this overhead if you just loop and roll. And as we've seen in that previous example, it's quite common to both loop and roll and software pipeline the code. So that's, you know, those techniques were popularized with the FPS system, right? That was a wide VLIW, and with math libraries handwritten, they do those techniques for classic loops. But to think about applying VLIWs to more general purpose code, the problem there is, what if there are no loops? And in particular, what if those loops are not vectorizable, right, in a simple way? Because notice that the VLIW machine, you can only do those tricks if those loops were basically vectorizable, if the loop iterations are independent. So if you look at, you know, twisty general purpose code, you know, branches really limit the size of each basic block. And it's really difficult to find instruction level parallelism within each of those little basic blocks. They're only 6 or 7 instructions long. They have some latency, they have some dependencies. if you had a 6 or 7 wide VLIW, it's hard to see how you could possibly make use of that if you just look at one basic block at a time. So the idea of trace scheduling is to, instead of thinking about one basic block at a time, think about a path or a trace through the code. So now you're going to look for not just one block at a time, but what are the most common paths that the code takes through all the basic blocks you have. And in this diagram, these arrows, the weight of the arrow indicates the frequency of taking that particular path between the basic blocks. So this is the most heavily used path along here. So the general idea is you start with the whole program, you then find the string of basic blocks that represents the most frequent branch path, and then you take that whole path and you schedule that code as a unit. So you schedule this almost like a very large basic block. And the thing to notice, this works great as long as the code actually follows its path, but it will occasionally jump out and back in to that path. And so what you have to do is, as well as generate code that handles this case, the code has to handle if there needs to be an exit or an entrance. And so you add fix-up code at these sites. And actually what you usually do, instead of re-entering this schedule here, you'll duplicate the following blocks and create a separate trace that handles scheduled code down this path, for example. Question?
The compiler is choosing this trace statically.
Correct. The compiler is choosing it statically, that's right. So the question now is, how do you know what the common paths are? And the answer is that you have to do profiling or some kind of compiler heuristic, which would just be guessing statically which paths are likely. But commonly what you would do is you would compile the program once with individual basic blocks, but also with some instrumentation code. You would then run it with representative data sets as input, and calculate statistics on how often the different branches are taken. Then take that information and then recompile the code using that information to select the traces you would take through the code. Okay, question?
If there are a lot of dependencies on a particular trace, does this help much at all?
Right, so if there are a lot of dependencies on the trace, it can't really help at all. The hope is that by having a long enough trace, you will find enough parallel work to do to justify the effort you put in, right, to doing this. So this concept was developed by Josh Fisher at Yale in a project there. They built a thing called the Bulldog compiler with his student Ellis. And so this idea then led to people wanting to commercialize this. And so this seemed like a great advance, actually, this advance in compilation technology. And so Josh Fisher led the creation of this company called Multiflow. Multiflow was commercialized to build very large VLIW systems using trace scheduling. Now some of the problems with this classic VLIW style. So the classic VLIW style has all the interlocks are exposed to software, all the hazards rather are exposed to software, so software has to provide the interlocks. Also the size of the instruction word is exposed to software, and the software has to schedule for a fixed size instruction slot, fixed size instruction word with given instruction slots. And the problem is you would have to recompile the code for every new machine or every new generation of machine. So this is kind of almost the antithesis of the IBM 360 model, where you have a standardized, say, with many different implementations. Here the compiler is very much aware of the microarchitecture of each implementation, and you're regenerating binary code for each of those instances. And what's worse is even for two machines in the same generation, you'd have to recompile the code. So the Multiflow trace was actually sold in 7-issue, 14-issue, and 28-issue variants. Basically had a single board that did a 7-issue, and then you would have either 1, 2, or 4 boards in a given instance of the machine. But you'd have to have different compiled code for those 3 different styles of machine, right? Different widths of machine. And every time a new machine would come out, everything would change. You have to recompile to get a new binary for the next generation of machines. So this is a problem in a classic VLIW. Another big problem is that even with all this work in scheduling and loop unrolling, software pipelining, most of those slots are going to be no-ops. That's just a fact of life in VLIW design. And so you need some way of dealing with this object code size. And so most VLIWs, most practical VLIWs had some form of compression on the object code to compress out the no-ops. Another big problem is this all relies on the compiler knowing statically the latency of all the operations in order for it to do the scheduling. And in practice, caches and memory bank conflicts, they give you unpredictable variability, things you just cannot predict statically because they depend on data that the program's running on, okay? So that makes it hard for the scheduler to do a good job. Branches in particular are usually a lot of branches are predictable statically, but there's enough that are not predictable statically that's a significant problem with static scheduling. Another issue is that you're relying on profiling, for example, to determine those branch probabilities, and profiling relies on your input data sets being representative. And if your user then runs at a different input data set that doesn't match the ones used to build the binary, they're going to see poor performance because it's going to go off trace a lot of the time. What's worse is, that's a problem, but what's even worse is some applications have, say, 2 phases, where a given static branch goes one way half the time and one way the other part of the time. So it's kind of trivial for the dynamic predictor to learn that. But if you have to hard code which way you go into the binary, you're kind of hosed as a static compiler developer. So it's really hard to work around. So I just want to go over a bunch of the techniques people did so the classic VLIW is sort of a very pure approach. In practice, it's not very practical to build machines for those reasons. So I'll go through some of the techniques people came up with to kind of handle those issues in real deployed VLIWs. So this idea of code compression. So one idea is that you store the VLIW instructions compressed in memory, where you compress out all the no-ops. And only when you do instruction cache refill do you uncompress it and store it uncompressed just in the iCache. And so then all the instruction slots are lined up with the functional units in the iCache, and so you have a very low latency path to get bits from the instruction cache and stream them directly to the functional units, but out in main memory, all the no-ops are compressed out. So that's what the multi-flow trace actually did. That was the scheme they used. One problem this causes, though, is that because the program is compressed in memory and branches are 2 whole instructions, it's difficult to map from the PC. When you get an instruction cache miss, you have to determine for the PC you're trying to fetch, where is it in memory? Because now you've got this variable compression scheme out in main memory, you have to go find it. And so there's usually some level of indirection from a PC to find where the compressed code block is out in memory. A different technique you can do is, instead of having a fixed sized instruction packet that you send to the functional units, is you allow it to be variable sized and just hold the instructions that are not no-ops. So don't hold no-ops in the instruction encoding. And so several machines have this style where they would mark a parallel group as being the set of operations that can go together in parallel down the VLIW pipeline. Okay, so the TI has a set of DSPs, the C6 DSPs that work like this. And the Intel IA64, we'll talk about, the Itanium design also does this. So they kind of separate out the unit at which operations are fetched from memory from the group of operations that can happen in parallel. Yep, question?
You would cache the branch results, though, wouldn't you?
Sorry, question is you would cache the branch results.
The problem of looking up an address for a branch that's in compressed memory, you would cache that.
Right, so the question is, if you had this compressed format in memory, would you not cache the locations of the branches? But remember, you're going to main memory and you get a cache miss. So it's for any cache you built would not be much bigger than the instruction cache you had on chip. And you have to cache all of off chip instruction memory. And basically build a table that you can cache the entries in that table to some degree. You could do that. But the thing to realize is this is after the cache. So you've already captured locality within the cache. It's for branches that miss in the cache. Or just sequential code, you drop off a code block and you have to go find the next line out in main memory. So this is manageable. It's just adds more latency. In practice, it adds more latency to iCache refill when you do that. Another simpler technique was used in the Sidra 5, which I think you're going to be reading about too. So the Sidra 5 had 2 kinds of VLIW instruction. Had a wide one and a narrow one. So the wide one was 7 operations in parallel. And when there wasn't enough ILP, they switched the sort of bit in the instruction encoding, said do those sequentially. So you either did them all in parallel or you did them all sequentially. So if there's no ILP, the 7 operations are just one after the other. So basically, the compiler would just determine for any given code was enough ILP to warrant using the parallel execution as opposed to serial execution. So we kind of really have to talk about Itanium if we're talking about VLIW. So this was Intel's way of getting rid of AMD as a second source for 64-bit architectures, was change the ISA completely. Also, they thought, HP, who were their collaborators here, wanted to get rid of their fabrication plant and have Intel fabricate processors for them. So these guys got together to come up with this thing called Itanium. And they called this style of computing EPIC, explicitly parallel instruction computing. It's really just VLIW. So terminology, IA64 is the ISA definition, and it was designed to be an object code compatible VLIW, right? So unlike the classic VLIW, the notion was a single binary would live between generations of machine. Merced was the first implementation. It was supposed to come out in 97. It was 4 years late, came out in 2001, and performance was abysmal. It didn't really work very well at all. This was Intel's implementation. HP did an implementation called McKinley, which was much better, which shipped a bit later. And they're still making these. So this is a relatively recent one, Pulson, 8 cores, very large chip. This is over 3 billion transistors and over 500 millimeters squared and 32 nanometer CMOS, 32 megabyte shared cache. So now Intel is still making these, but they're kind of resigned to the very high-end server market and basically satisfying HP's requirements for processors. Just to talk about some of the things they did there, in Itanium, they had the 128-bit bundle was a unit that instructions were packed in memory, but that was orthogonal to the parallel instruction groups, which could be just one instruction slot here or multiple instructions spanning many bundles. And they did this to make this object code compatible VLIW. And so the notion was you could build a hardware microarchitecture that could execute one or more bundles in parallel per cycle at peak, but it would read the bundles from memory, and the groups could span many bundles. So if you had a wider Itanium, you could issue all of these at once. If you had a narrower one, you could take this long parallel bundle and just do it one at a time sequentially on however much hardware resource you had in that implementation. Now, one constraint that added, though, was going back to the write after read hazards within a single VLIW instruction. So for Itanium to enable the low-end implementations to do the operation sequentially, you had to remove that. So none of the instructions in a bundle could write a register that another instruction, the same group, none of the instructions in the same group could write a register that another instruction in the group would read, because you want to give freedom to implementations to do these in any order. I'll skip through. It had a lot of registers. So one thing is when you do compiler-based loop unrolling software pipelining, there's no register renaming. There's just a lot of architectural registers that the compiler does the renaming in effectively. And one very interesting trick that people use in these loops is called rotating register files. And the problem you're trying to solve is when you schedule those loops, they take a lot of registers and a lot of duplicated code. Also in the prologue and the epilogue, you notice you have to load up the pipeline with subset the operations being valid. Then you have that central piece that iterates for a while. Then you have to drain the pipeline. So you end up with a lot of duplicated code. And so the solution is rotating registers. We allocate a new set of registers for each loop iteration. This is a very, very simple way of doing register renaming. Basic idea is you have a base register number, rotating register base, and you add this number to the architectural register number of the register of the current instruction to get which physical register you're going to touch, right? So it's just an addition to the architectural register. So if you have that bit of code we had before in the loop, you would say load into F1, and these would be from different loop iterations, and then the closing instruction here would not just branch to the loop instruction, it would also bump that rotating register pointer. So you change the add value. It's easiest to see this when you unroll it a little, but basically the latency between this load and the add that will consume it is encoded as the difference in the architectural register numbers. So loading into F1, after several cycles later, you're going to change the pointer. So F1 will now be F4. And so this pointer is going to decrement. So when this instruction reads from F4 sometime later, that will actually be F1. The physical register F1 was loaded into here. Similarly for store latency. So this is the base pointer here. Just it's easy to see this when you write it out. So this is the thing to remember, this is one instruction in instruction memory. As you execute it, its meaning changes based on this base pointer changing. Right, so when the base pointer is 8, this F1 maps the physical register P9, and so on down the list. So when you load P9 here, this use from F4 in the add will be P9 by the time the base pointer goes down to 5, right? So this load here will translate into the use here. So this is how you use rotating registers to cut the code size. So notice, instead of having to explicitly represent this in the instruction stream, you have one instruction in the instruction stream and this dynamically changing base register to do the rotating register. Okay, so that's the notion of rotating register files. Okay. So the way to avoid branches, one problem with branches is they cause changes in control flow. But in Itanium, basically, as in other earlier VLIWs, the idea is to use predication instead. You just mask off, you would set a predicate, and then do conditional execution under the predicate. And this is very important for VLIW machines when you want to combine multiple basic blocks. Here's an if, then, else piece of code with a branch condition here. Basically, you can compress all this into a single new basic block where the branch turns into setting predicates. And then you can actually co-schedule both basic blocks to happen at the same time with just the predicate selecting which operations actually take effect and write back to the machine. So you can remove about half of the branches. Though a later paper showed that the performance benefit of this was actually very minor, it turned out, but I just want to skip ahead. So there's a bunch of other features added to Itanium. You should go read through the slides on speculative execution. Actually adding hardware, supporting the hardware to allow the software to do speculative execution. For example, you have a load after a branch, and you don't usually want to do this load unless you're sure about the branch, because it might cause an exception. But they provided a technique that you could indicate the load was a speculative load, so it wouldn't cause an exception here, but when you got to the target of the branch, you could check to see if that load had caused an exception. So I won't go through this technique, but they added a bunch more features in the hardware that had software interfaces, so software could drive this. And as a result, the instruction set was incredibly complicated. They had like many, many features that the compiler could drive. So this style of VLIW machine is not a simple VLIW. It's very complicated. It relies on a complex compiler, understanding this complex ISA, understanding the microarchitecture, and scheduling things to do things right. And as a result, VLIWs basically failed in general purpose computing. So they really don't fit general purpose computing very well. And the big problem is really things are too dynamic, and the simple predictors can determine these things much better than any kind of profiling or static, inherently superior. And building superscalar architectures kind of know how to do that, and they work well. And also, as you start making the VLIWs be more complicated and have more of those features like code compatibility and compression and things, in terms of complexity, they're very similar to just in-order superscalar machines. And in-order superscalar machines, the advantage of being compatible with out-of-order machines too. So you can have one ISA. If you decide that you just want a simpler microarchitecture, instead of doing a VLIW, which is a different ISA with all these problems, just build a dynamic in-order superscalar, and that will give you that simpler machine. The only place VLIWs really persist is in embedded DSP, where a lot of things are more statically known, like the memory hierarchy is statically known. You're doing simple loops where the branch paths are well known. So they kind of have a place here, but in general purpose computing, there's been many attempts and all of them have failed, basically. So, VLIWs are kind of a bust for general purpose computing.